Hi, I'm Olsi. Today is Monday, 13th of November. We're going to be doing an honors physics experiment for physics 253. This experiment we will be discussing about Hooke's law. As you can see, we have a couple of strings over here. We have in total of 1, 2, 3, and 4 strings. So for the first 3 strings, we will be adding several different weights on them, and we will take the displacement and write it down. So some springs will have a bigger spring constant, whereas others will have a smaller spring constant. And that's something we're going to be observing as we will be adding weights. So after getting our data down, we will make a graph, which we would expect for it to be a linear graph. And after we get our graph, we can finally calculate our spring constant by using the formula F equals negative K times X. And on our fourth trial for our fourth string, which is going to be this one that I got by myself, we will test our spring and then extend it enough so that its deformation will occur. And by deformation, I mean that the spring will remain to a permanently deformed state or shape. Alright, starting up. So this is our first spring that we're going to be using. So for our setup, we have Logger Pro setup over here. We have several different weights, as you can see. And then we have everything set. So we will start by taking, this is going to be our equilibrium state after we remove this one weight. Okay, now we'll click to Logger Pro and collect our data. Okay, as we can see, our position is going to be 4.29 meters. We will grab a pencil and write this down. 4.29 meters. And now we'll add a small weight. This is going to be 20 grams. So that would be 0.02 kilograms. And now equilibrium. So now we will collect our data once again, and we notice that it has went down to 0.399 meters. We will also write that down because we will have to draw a graph. Okay. Now we will add some more weight to it. We will add another 20 grams. Actually, let's make it interesting and add some more to it. Let's add 40 grams. Okay. Now we collect our data. And we see it went down to 0.351 meters. And it went down to 60 grams now. Okay. And now for our final point, we will add some more to it. Another 20 grams. Okay. We collect once more. And it looks like it's gonna go down to 0.317 meters. And our total mass now went down to 80 grams. Okay. Alright, now that we got our measurements for our first couple of displacements, we will go on the board and actually try to graph it. So we actually already got it written down. So for our equilibrium point, which the position would be 0.429, this is going to be 0 because this is our equilibrium point, like I said. And then if our displacement from this point to this point, so for 0.429 to 399, we have a displacement of 0.03 meters, and that happened by adding 0.02 kilograms on of mass, and that is going to be equal to 0.196 newtons, because the formula would be F equals m times g, because it's a vertical motion. Okay, and then we had another 2 displacements because we added 20 kilograms. The displacement for that was 0.078 meters, which gave us a total of 0.588 meters. And then we added another 20 kilograms, so that we have in total a total of 0.080 kilograms, and that gave us a displacement from the equilibrium point 0.112 meters, and our force here was 0.784 newtons. Now we can actually graph this. So we have our points written down over here, and then as we can see over here, for this displacement, our force was 0.196. So we can actually write it about somewhere around here, 196, and this would be somewhere here. Now for 0.78 we had 0.588, so this would be somewhere around up here, like 8 newtons. This would be somewhere here, and then 0.784 newtons. This would be slightly above this point, so 7, 8, 4. And now we're going to connect these dots and expect for this line, or hopefully be a linear graph. Okay, these are graphs. So for this experiment, we also had to create a linear fit in order for us to represent the force and the displacement. So as you see over here in this Excel sheet that we created, we have the force versus the displacement. We have force on our y-axis and then displacement on our x-axis. So the reason why this is not a perfect line is because the body was still oscillating, and as I was taking the measurements, I didn't wait long enough for it to completely stop. Now if you zoom in a little bit, you can realize that there's an equation in there. So as we see, the 7.1772 is our slope, which gives us our k constant, and that sums it up for our Excel sheet. First displacement, we only added 20 grams, so that would be 0.02 times 9.8, which is our gravitational force here, over 0.03 meters, which was our displacement, and we got a total of 6.53 newtons over meters. For our second displacement, we did the same thing, and we had a total of 7.53 newtons over meters, which was slightly above what we got for our first displacement. And then for our last displacement, we got 7 newtons in total. So as you can see, they're all pretty much within one difference. And then lastly, we got the average for all three constants that we had. So that would be 6.53 plus 7.53 plus 7 over 3. And that got us the average. So our average spring constant was 7.02 newtons over meters. Now moving on to our next trial, we have a completely different spring. This spring is definitely smaller than the previous one, but it's not. This is not the only difference. There's another difference. It's the fact that it's spring constant. As you can see, I'm trying to extend it, but it's not extending. So its spring constant is way bigger than the previous one, and we can actually test this. So we will start by adding 20 grams like we did for our first spring, and we will notice difference. So this is 20 grams. As you can see, it didn't move at all. We're gonna add another 20, and as you see, it doesn't change at all. Having all 20, it didn't move an inch. So previously we had a total displacement of almost 1 meter. I mean, almost 0.112 meters. But this time we don't have any displacement at all. So now we're gonna try to add some heavier weights on it. We will try adding 0.5 kilograms, and it's slightly changed. Now we will try to use Logger Pro and see how much it actually changed from its initial position, which was, I'll have to stop this. And now, so the equilibrium position would be roughly 0.559 meters, and now we will try and add 0.5 kilograms and see by how much it will change. Okay, so we got 0.522, so it roughly changed about 30 centimeters, which is not so much. We will try and add some more and see. We will add another 200 grams. No, this one. So adding another 200 grams would move it slightly lower. So this gives us roughly 0.5 meters. Okay, so as we can see, observing how different springs have different spring constants, this one definitely had a way larger spring constant than the previous one. So we will try and use another spring for our last trial and see how things can change if we fully extend the spring. So showing you this spring over here that I brought. So this is also a pretty hard spring, but we will try and extend it and see what happens if you extend a spring beyond its elastic movements. Okay, so we will start by adding 0.5 grams, 0.5 kilograms. It didn't move an inch at all, but we will try and add as much as possible and hope for the best. Okay. We just add another 200, an extra 200, another 200. It's slightly bending. As you can see, it's going down. We'll have to add some more. Okay. We'll try and find another 200 one right here. Alright, and now as we see, we had to change our setup because we didn't have enough mass for this spring. It's kind of stubborn because we need to add a lot of mass on it, and the spring constant is definitely way bigger than the previous trials that we had. So we will try and add some more weight. We will have, or currently we have about 0.5, 0.2, so 0.7 plus 0.9, we have 1.1 kilograms. And now we're gonna go up to, we're gonna add another 200. Okay. We're adding another 200. Okay. Another 200. Right, so we are about 1.7 right now. Now we're gonna add some more to it. And hope for the best. Now we're gonna go on the other side and add some more. Okay. It looks like we need to add some more to it, so hopefully this, nope, not yet. Now we're gonna add another 100. It's still not there yet. Okay. This hopefully does the job. It doesn't look like it, but we're gonna add some more because we have plenty of weights. As you can see, it has went down from its equilibrium point by a lot. We will try and add another 100. This is getting kind of risky, but we're still managing to stay safe. We'll add some more over here. Oh gosh. Okay. Probably should stop soon, but we're still gonna keep going.
So, if you notice,
We're gonna add this another 100 grams. And as you can see, right at this moment right here, we realized that the spring did not go any lower from its original position. So that means that we've reached our maximum K constant, so which means that it's not gonna go any further lower. So we're gonna remove all of these weights and see if the spring has deformed at all. We gotta be careful over here because this is a lot of mass. This gonna take a little while, I'm sorry about that. Okay. So looking back to it, if you can zoom in, we see that it has slightly changed because, as I said earlier, we saw that we were kept adding mass to it, and the length remained the same. So that's how you know that Hooke's law has reached its maximum extension possible. So as we saw earlier, after adding all of this mass over here, which was roughly about 2 kilograms, it didn't change much as we see over here, but now we use this over here. You see this drastic change from what it was originally. So we're gonna test it out real quick and see how the spring is gonna deform. So we're gonna like hang it from here and then try and push down, and we're gonna see how it slowly deforms. So right over here we see that the spring has lost its ability to go back to its original position, and how much it has changed from what it originally was. And this concludes our experiment. Thank you for watching.